This is the last lecture of this Physics 218 course. Erwin Schrodinger, 1887 to 1961, Austrian physicist, best known as one of the creators of quantum mechanics. His approach was shown to be equivalent to the Heisenberg uncertainty approach. He also worked with statistical mechanics, color vision, and a little bit with general relativity. He received the Nobel Prize in 1933, and he was kicked out of Oxford because he lived with his wife and his mistress. A lot of times I give you information that may not be true, but this actually is true. Kicked out of Oxford because he lived with his wife and his mistress in the same place. You might have said, at least from his perspective, that he was in a superposition of undefined states. So, since de Broglie received the Nobel Prize in 1929 for what he called matter waves, Schrodinger received the Nobel Prize in 1933 for proving that waves matter too. How about that? The Schrodinger equation has been extremely successful in explaining the behavior of atomic and molecular and nuclear systems, whereas the classical physics failed to explain this behavior. Many of the phenomena that we now know in electronics is a result of Schrodinger-type quantum mechanics. Furthermore, when quantum mechanics is applied to macroscopic objects, the result agrees with classical physics. In other words, this is called the correspondence principle. If you actually increase your n value up to the point where it would be macroscopic, then you have classical physics. Solutions of the Schrodinger equation may be very difficult. We're going to look at the time-independent Schrodinger equation. And as it applies to a particle of mass m confined and moving along the x-axis and interacting with its environment through a potential energy function u of x. So we always have to think of the combined wave function with the particle and its environment. It looks like this. Negative reduced Planck's constant h bar squared over 2m times the second derivative of the wave function with respect to x plus the potential energy times the wave function equal to E times the wave function psi. This is called the time-independent Schrodinger equation, and it looks somewhat intimidating, but if you break it down and you look at this, the second derivative of psi with respect to x is actually going to give you a k number, a k value, and you're going to have h bar squared k squared, which actually is going to be your momentum squared over 2 times your mass. So really this first term is actually another way of expressing kinetic energy. And the second term, of course, is potential energy. So we'll just have kinetic energy plus potential energy is equal to our total energy. It's really the one equation, the rule of all, that we introduced in Physics 1. It is the conservation of energy equation. And Schrodinger, applying it to quantum mechanics, the one equation, the rule of all, it is a Nobel Prize winning result. How about that? The one equation, the rule of all. Let's apply it to what is called the particle in a box, or also called the infinite square well. Infinite square well, we have a potential that is actually 0 between 2 points, 0 and L, and then infinitely large elsewhere. We're going to start with the Schrodinger equation. Negative h bar squared over 2m, second derivative of psi with respect to x plus u psi equals E psi. In the region from 0 to L, we have no potential energy, 0. So the Schrodinger equation simplifies with no potential energy there. to just being the second derivative of psi with respect to x is equal to negative 2 mass energy over h bar squared psi, and we can think of this as being a constant. So it's the second derivative of psi with respect to x is equal to negative some constant times psi. This is a second order differential equation. In this case, our constant k is equal to the square root of 2m energy over h bar. If you recall, the square root of 2 times the mass times the energy is often, at least in relativistic terms, referred to as being the momentum. So k is equal to the momentum divided by h bar, or you could say the momentum is equal to h bar times k. This is very reminiscent of our wave equation that we had back in Physics 2 in Chapter 18, where we were describing simple harmonic motion. We have the second derivative of something is related to that something. And the solutions of that wave equation back in Chapter 18 were sinusoidal functions. So the solution of this wave equation is also sinusoidal. Psi of x is equal to a sine kx plus b cosine kx. We can determine our constants a and b by our boundary conditions and our normalization conditions. In particular, we do have boundary conditions in this case with our infinite square well. We know that with this large infinite potential at 0 and L, that we should have nothing at x equals 0. The wave function should terminate at that point because it cannot go beyond that wall. So this forces our psi of x, psi at 0, to be equal to 0, where x is equal to 0. If I put that into our solution here, we would have, well, sine of 0 is indeed 0, so this first term is gone. But the cosine of 0 is 1. So we're going to have that our b constant should be equal to 0 in order to make that work according to the boundary condition. So the b term is gone. B has to be 0. So now we're just left with our wave function equal to a sine kx. It should also meet the other boundary condition. We know that this wave function should also be 0 where x is equal to L. So if we make x equal to L, this forces k times L to be equal to an integral number of pi, such that the sine function will be 0 at that point. Hence, k is equal to an integral number of pi divided by L. And now our general solution looks like psi of x is equal to a sine n pi x over L. But if we were to normalize this, we know that the particle should be found somewhere. And if we integrate it over all x, then the probability density integrated over all x should give us a definite particle. So that probability should be equal to 1. We'll find it somewhere between negative infinity and infinity. But we already know that it's not allowed to be less than 0 and greater than L. It's confined into the box. So we can actually reduce our limits in this integral between 0 and L. The probability density integrated between 0 and L should also be equal to 1 because our particle should be found inside the box. Well, if we put our wave function in there, we now have from 0 to L integration a sine kx squared dx equals 1. Take out our constants. If we integrate sine squared kx dx from 0 to L, we can look this up in a table of definite integrals. And we would have that a squared times our solution for this, 1/2 x minus 1/4 sine 2kx over k, from evaluate from 0 to L, should equal 1. Well, if I put the L in there for our x, and I substitute in for k, which is n pi over L, in the numerator here, our L's will cancel out, and we're going to end up with sine of 2n pi. And the sine of 2n pi is actually going to be 0 because n is an integer. So that's going to be 0, and this whole second term here will be 0. And we are now left with a squared times 1/2 L equals 1. solving for A, bringing the 2 and the L over to the other side, taking the square root, I have A is equal to the square root of 2 divided by L. So now my normalized wave function is A, which is the square root of 2 divided by L, sine n pi x over L. That is the wave function within the zero potential area between 0 and L. Note that k is equal to n pi over L, and we earlier defined it as the square root of 2me over h bar. With a little bit of manipulation of these, noting that h bar is equal to Planck's constant divided by 2 pi, we would get, with a little bit of solving for E here, squaring both sides and solving for E, that the energy of our nth level would be equal to h squared, n squared over 8 times the mass times L, n being an integer, and we would have basically that our energies are quantized. There are definite levels of energy that correspond to this particle trapped inside the infinite square well. This is exactly the result we got using different considerations before treating the same problem of the infinite square well. How about that? Much easier here using it Schrodinger's equation to solve for it. So we end up with these wave functions trapped for a particle in a box. Wave functions are constrained to be 0 at the boundaries, at where the potential goes to infinity. And then we have our different wave functions for n equal 1, n equal 2, n equal 3. And then if we found our probability densities for n equal 1, 2, 3, and so forth, we'd find that under different energy levels, the particle would be found at different places with also points of nodes as well. As the n value goes up, there's more probability that the particle could actually be found near the walls. We are constrained for our probability density to be 0 at the boundaries and 0 at specific node locations as well, depending on the values of n. As n increases, the number of 0 points increase each time proportionally. Recall what our treatment was for standing waves on a string in Chapter 18. The ends of the strings were, in fact, nodes, constrained, and hence we found that the wave functions must be 0 at those ends, and that led to a specific wavelength and frequency that was allowed for standing waves. And they were integer multiples. So we found that for standing waves on a string, for resonance on a string, the frequencies that correspond to those standing waves were indeed quantized. Well, we have a similar thing here. A particle in a box. The particle cannot exist outside the box. The wave functions were 0 at the walls. And fitting the de Broglie wavelengths into the box led to quantization of the frequency as well, and in this case of the momentum and the energy as well as going along with that. So the difference is the quantum particle is much more complex than waves on a string, and the quantum particle has these quantized energies. But the idea is the same. Once we introduce boundary conditions to a particle, we introduce quantization. Only possible energy levels and not continuous energy possible. More common than an infinite square well or a particle in a box would be a finite potential well. This is actually more of a practical application in modern science. But it's very similar to what we just did with the infinite square well. In this case, we could have an energy that is somewhat less than the potential energy at the walls here. And so the particle will have this energy in region 2, but they'll have a lesser energy than the walls in region 1 and region 3. So we have potential energy of 0 in region 2, potential energy greater than the energy of our particle in region 1 and region 3. According to classical mechanics, if the total energy E of the system is less than the potential energy, the particle will be permanently bound in the potential well. It can never have energy greater than that, the potential energy of the walls, and it would be permanently bound inside the well. If the particle were outside the well, its kinetic energy would be negative, and that would be impossible as far as classical treatment would go. But quantum mechanics is different. According to quantum mechanics, there's a finite probability that the particle can be found outside the well, even if its energy is less than the energy of the walls. The uncertainty principle allows the particle to be outside the well as long as the apparent violation of conservation of energy does not exist in any measurable way. So, looking at this problem, if we look at the region 2, the middle region, where our potential energy is 0, the wave functions there will be sinusoidal, like we found with the infinitely square well, or the infinite square well particle in the box example that we just looked at. But the boundary conditions now no longer require that our wave function goes to 0 at the ends of the well, because we don't have an infinite potential well. So the general solution, at least in this region, will be one of a sinusoidal, f sine kx plus g cosine kx, and we don't lose the g this time because we are not going to 0 at our boundaries. If I look at regions 1 and 3, where the potential energy is greater than the energy of our particle, the Schrodinger equation for these regions would look like this. Second derivative of psi with respect to x will equal 2m potential energy minus energy of the particle over h bar squared times psi. Again, the second order differential equation. And the general solution in this sense would be a e to the cx plus b e to the negative cx, where c is the square root of 2m u minus e over h bar squared. Well, if I look in particular at region 1, I want to make sure that this wave function is finite, and especially when we go to large values in the negative direction of x. So when x approaches negative infinity, we don't want this thing to blow up. So that would ensure that our b constant should be 0 in this equation, because if x were negative infinity, we'd have e to the infinity, and we can't have that happen. So our b is 0, and hence in this region, the wave function is simply a e to the cx. In region 3, we want a similar idea, only we don't want it to blow up when we go to values of x that are infinity, positive values of x. So we can have b now, but we can't have this first term where a is equal to e cx, where x goes to infinity, because that will blow up the wave function. So we want a to equal 0. Hence, we're left with our wave function b equal to b e to the negative cx in this region, region 3. We can solve this now because we have wave functions in all three regions. We have constants in these equations, and they must satisfy our boundary conditions at the boundaries and the normalization condition. Boundary conditions are at x equals 0. The wave function should be continuous, so wave function psi 1 should equal psi 2 at that boundary, and it should be true that the derivative of the wave function should be continuous as well. So d psi 1 dx will equal d psi 2 dx. That would help us determine the coefficients of the wave functions in these two regions. And the same thing will apply to the other boundary conditions at x equal L. We should have a continuous wave function, psi 2 should equal psi 3, and the derivative of our wave function should be continuous across that boundary. That's how you would solve this problem. It's a little bit more complicated than the one we just did, so we're not going to do it here. It's something you could do if you had some time on your hands. You're not going to be required to do that, but it just shows that these are problems that can be solved using Schrodinger's wave equation. Some of these problems get much more complicated, but they are indeed solvable using linear algebra and mathematics derivatives. Here are results for our first few wave functions. We can see that, like the infinite square well and particle in the box, we have wave functions that vary in form as our values go up in energy. But here we have a finite possibility of the wave function extending beyond the potential well. So outside the potential well, classical physics forbids the presence of the particle. In quantum mechanics, the wave function exists and decays exponentially to approach zero. Here's a finite potential well, graphical results for our probability density. And again, it looks very similar to what we had for the infinite potential well, but again, there is a finite probability that the particle can be found outside of the box, smooth at boundaries. Here's an application of a finite potential well. Nanotechnology refers to the design of devices having dimensions ranging from 1 to 100 nanometers, and one design of that would be the quantum dot. Quantum dot is a small nanoscale region that acts as a potential well, trapping a particle, be it an electron, a photon, an exciton. Exciton is a electron hole pair. And so as this quantum dot gets smaller, the possible energy levels get larger energies between their levels, and allowing you greater energies for the emission of photons. But there are definite discrete values for those energies. So if we had a colloidal solution of quantum dots, as we reduce the size of the potential well, the length of the energy gaps gets longer, and we can have more energy in those photon excitations. Hence, as our size of the well gets smaller, the kind of visible energy you would see will get greater, and as we go from red to blue in this case, and we can actually get a nice pure value of that color by limiting exactly the size of our potential wells. And this is something, probably by the time you see this lecture and beyond, something that's going to be incorporated in our technology very soon in things like pure color displays and that sort of thing. So this is all quantum mechanics. It's the theory of quantum mechanics. But like other theories in science, they're very strong. They're not like theories in the courtroom where you might have a theory and you might be able to prove it wrong based on a preponderance of the evidence. Here in science, if you have a theory, it hasn't been proven wrong. If you prove it wrong, you got to throw it out. Or else you have to make a modification to your theory to incorporate your exception. So this quantum mechanics has no exception so far. It's based on the idea of probabilities, finding a particle, 40% over here, 60% over here, and dealing with that situation in electronic applications. If you don't like quantum mechanics, if you don't like the theory of quantum mechanics, you might as well start throwing your nice smart devices out, because much of the technology that goes into these devices is based on the theory of quantum mechanics. Things like tunneling and storage devices, your flash drives, is based on the tunneling mechanism of going through a barrier. Classically, it's not possible. Quantum mechanically, it's possible for a particle to make it through a barrier and be recorded in memory. We're discussing Schrodinger, and I think a treatment of Schrodinger wouldn't be complete without touching on a very famous instance of Schrodinger, and that's Schrodinger's cat. It's very popular in pop culture. And the situation, it's been referred to in things like the Big Bang Theory show on TV and other things to relate trying to find an outcome based on just doing things. Here's how it works. We place a living cat into a steel chamber. Very smart cat, Schrodinger's cat, because mew, because he happens to know what the coefficient of friction is. So he indeed is Schrodinger's cat. There's a small bit of radioactive substance in this chamber, and so there's some kind of probability that that substance is going to decay, but we don't know exactly when it's going to do it. If this substance decays, if even a single atom of the substance decays, it's going to trigger a mechanism, a relay mechanism, and that will trip the hammer. The hammer will break a vial of hydrocyanic acid, and the result of that would be to kill the cat. So, yeah. Now this is proposed by Schrodinger. The observer cannot know whether or not an atom of the substance has decayed, and consequently whether the vial has been broken, the hydrocyanic acid has been released, and the cat killed. Since we cannot know, to us, the cat is both dead and alive, according to quantum law, in a superposition of states. It is only when we break open the box and learn the true condition of the cat that the superposition is lost and the cat becomes either one or the other, dead or alive. So the cat will exist in us in a probability of states, either dead or alive, some probability of each, but we can't really know until we break open the box and look for ourselves, at which point that superposition is lost and the quantum superposition is lost and we actually know the outcome. This situation is sometimes called quantum indeterminacy or the observer's paradox. And it kind of goes like this. The observer's observation itself affects the outcome. It can never be known what the outcome is or what it would have been if it were not observed. The fact that you go in to find the outcome determines and finally determines the observation for you. But you can't know what it would have been before that observation. It still would remain in a superposition of states. Like I said, this has become famously an example in pop culture. For particle interference, a single particle can then be in multiple places simultaneously. An electron, as we saw in electron diffraction, can go through either slit. It's only when we try to focus in and find out which slit it actually goes through is when it actually goes through one or the other. But before that, it goes through both. What this fact implies about the nature of reality on the observable level, macroscopic level, like cats, as opposed to small things like electrons, is a very sticky area of quantum physics. Schrodinger received a lot of flack for this example. He was trying to explain quantum indeterminacy, and he received a lot of flack for this example. It's become popular, like I said, in pop culture to explain things like human relationships. You never know unless you try, and then you never know what the outcome would be, that sort of thing, in the Big Bang Theory. But since Schrodinger received such grief over it, at some point he said, "I wish I had never met that cat," because he was tired of dealing with this situation. Here's my corollary to the Schrodinger cat. Here's Schrodinger's dog. He's a cute dog. You like that bone, don't you? Don't you? You like that bone. Yeah, you do. Yeah, you do. You want to give me that? No, you want that bone, don't you? So cute. Such a cute dog. Now let's find out when we have. You thought I was going to hurt that cute little dog, didn't you?